Hello guys, welcome to my first video where I'll be talking about fins. My name is Daniel and I'm a third year chemical engineering student. This will be a very thorough video where we will go through the complete solutions of a fin problem. If you feel comfortable with some of the concepts that we go over, feel free to access the timestamps at the description of the video down below. So what are fins? Fins are heat dissipating elements that increase the surface area of whatever element you're trying to cool down or heat up, and they are used in a wide variety of applications, including circuits and pipes. They are very important in chemical engineering and in heat and mass transfer. To better understand fins, let's look at a problem. I'll give you 2 minutes to pause the video and perhaps even start the problem by yourself. Okay, so I'm assuming you already paused it. So what do we know about the problem? We know that we have this pipe containing steam and we wish to cool it down using this annular fin. Notice that the temperature of the pipe will be different along the axial direction. However, we don't care about how the pipe temperature changes along the pipe. We already know the temperature at the interface of the fin. We are interested in finding the heat rate dissipated by the fin, and for that we just need to know the pipe temperature at this interface. Okay, so the first step to solving this problem is to list the things that we know. So what do we know? We know the dimensions of the fin. We know the properties of the surrounding air. Properties, and something really important is that we know the temperature of the base of the pipe at the interface. So temperature of the base. Okay, the next step is to write down what we want to find. So what do we want to find? It's here. What is the heat rate dissipated by the fin? So we want to find the heat rate. Let's call it QF. But what do we need to find the heat rate? We need to find the temperature profile. Temperature profile. Remember, Professor Servio usually says that if you know the temperature profile, you know everything. So usually the temperature profile is to find an expression that tells you what the temperature is in any point of this fin and at any time. And then 3, we're gonna list our assumptions that will help us simplify the problem. So the first one could be that we have steady state. And why is this the case? Well, from the problem statement we know there is no allusion to time. There are no time dependent properties. The system's properties don't change with respect to time. We don't know when this is occurring. This is a constant steady state system. Okay. What else can we assume? We can assume that the properties are constant. So the heat transfer conductivity, H, and the thermal conductivity of the fin, even though they are actually functions of temperature, we can assume that for the scope of this course and for the scope of this problem they are constant. So constant properties. We can also neglect radiation, which is only significant at temperatures higher than say 1000 degrees Celsius, which is clearly not the case of this problem. So negligible radiation. And one of the most subtle assumptions that will help us simplify this problem is that the fin is very thin. So why is this such an important assumption? Well, let me first show you the axis of this system, or the possible directions in which the temperature could depend on, and then we'll see how having this thin fin assumption will help us simplify the problem greatly. Which will lead us to having a single dimension problem opposed to 2 dimensions. So Let's write that down. Thin. Let us first draw the possible directions of temperature dependence. In this case, we will use cylindrical coordinates because they are the most convenient coordinates to use in this case. As you can see, the fin has a cylindrical shape, so that's why it's the most convenient to use. So this is the axial component, or the Z direction. This is the radial direction, so it goes outwards from the center, and this is the angle direction, theta. We need these three coordinates to completely specify any point in the cylindrical coordinate system. So the first thing to consider, can the temperature vary along the angle theta? Well, if you look at this problem, there is symmetry along the angle. As you can see, the temperature of the base is constant along the whole surface. So the temperature will be the same on this ring. That means that heat will just flow with symmetry along the angle. It'll flow equally outwards from every point. So it will flow like this, like this, like this, like this, and so on. Because of this, it wouldn't make sense to say that the temperature depends on the angle component. What about the Z component? So before we said that the fin was very thin. It was so thin that we can neglect the temperature gradient that could occur along the axial direction. So that means that the temperature along this, say this line here, is equal to the temperature, say along a line here on the center, and is the same as the temperature on this bottom line here. So that means that temperature, the isotherm, is basically a cross section of the fin, a complete cross section. In reality, there is a small thermal gradient along the axial direction. So this the central line that I drew is gonna be a little bit warmer, a little bit hotter than the one on the surface, because this one is more exposed to the ambient air, so it's gonna be cooler. However, if the fin is thin enough, we can neglect this temperature gradient and say that the cross section is basically a complete isotherm. So an isotherm is a complete cross section, like this. This is one isotherm. In other words, any point that has the same radius in the fin will have the same temperature, which makes sense to me. Let's draw another isotherm, say a closer one to the center, and now say let's draw the warmest isotherm of all, which is here on the surface temperature. So I already drew it. Notice that heat always flows perpendicularly to the isotherms. Since heat flows symmetrically radially outwards, the only shape that is always perpendicular to any of these arrows is just a circle. So it makes sense to think that isotherms are circular, or to realize that isotherms are circular. This leads us to the next step, which is setting up the differential control volume. So step number 4. Differential control volume. So the trick to drawing a differential control volume is to set two isotherms really close to each other, so close that the only difference between the two isotherms is just an infinitesimal increase along the direction of temperature dependence. So imagine this is that middle isotherm that I drew, and let's draw another one almost on top of it, really next to it. This one. Oh, oops. Just redraw that better. Here. And it actually looks kind of like a donut. This. And then this. Okay, drawing is just so bad. Okay, let's try that again. There we go. Alright, you kind of see what I'm saying here. Just imagine these two isotherms are just drawn next to each other. And now let's label the dimensions of the isotherm. So we have the axial thickness, the radial thickness, sorry, which is an infinitesimal amount, so dr. And notice that we can have infinite in differential control volumes. You could have drawn a differential control volume really close to the center of the fin, or close to the outer edge, because it's given by an infinitesimal thickness. So you can have as many as you want, and any one of them will completely define the fin as a whole. So from this differential control volume is where we get our property balance for the system, and from the property balance we will get our temperature distribution. So it's very useful to draw differential control volumes. What about the thickness? Will the thickness be any quantity different from the actual thickness of the fin? Not really, because we said that the temperature doesn't vary along the axial component. So the thickness of the differential control volume will just be the thickness of the fin overall. So this leads us to the next step, which is setting up the energy balance, the differential equation for the system, which comes from an energy balance. So differential equation. Okay, so to set up the differential equation, we have to resort to the holy grail of chemical engineering. It is the general energy or quantity balance that we all learn on our first day of chemical engineering. Usually goes in the form of in minus out plus generation equals accumulation. Okay, so what about this accumulation term? We can definitely cross this out, because we said originally that one of our assumptions was that we didn't have any time dependence. None of the temperature doesn't change with respect to time. There's steady state, so this is equal to 0. What about generation? Does the fin generate? Does it sink any heat? This could be tricky because as you may recall, we defined fins earlier as heat dissipating elements. We said that they dissipated heat, but that means that all the fin is doing is actually just increasing the surface area of whatever object you're trying to cool down. In this case it's a pipe. You're just increasing the surface area to expose it to have a higher amount of surface area exposed to the surrounding air, which is at a lower temperature than the pipe temperature. So by increasing that surface area, you're just enhancing heat transfer. You're not absorbing any heat transfer on your own. You're not keeping that heat. You're actually just transferring it to the surroundings. So this is equal to 0, and this leaves us with the trivial balance of in minus out equals 0. So we need to first find what are the heat rates coming in and what are the heat rates coming out. So let's start with the conduction heat rates. These are the ones that we just drew here that flow radially outwards. But notice that there is also another type of heat loss, that is the convection heat loss, that occurs between the fin and the surrounding air. But let's first start with the conduction one, which is the the one perpendicular to the isotherm. So we can draw it here as going from the center into the wall. This is Q evaluated at R, and then we also have heat coming out evaluated at R plus the infinitesimal increase dr. Right? So these are the two conduction heat rates of our differential control volume. And what about the convection heat rates? Well, they occur between two media, so the fin and the surrounding air, and they are expressed from Newton's law of cooling. We'll come back to this later. but let's label it first so we can show it as a vertical component. And notice that it's both the top and the bottom surfaces at which this heat rate occurs. Okay. Also notice that this quantity is a differential quantity. And why is it differential? Because it occurs on a differential area element, which is given by this dr term. Notice that this the inner cross section at which the conduction heat flow occurs is not a differential quantity, because the thickness is it's a finite thickness, it's T, and the inner surface and the surface area, like the inner cross-sectional surface, is also a finite quantity, which is given by 2 pi r, right? So that is why these quantities are not differential, but only this one is differential. And this will be relevant when we want to find expressions for these quantities. But so let's first start with the conduction heat rates. Let's find expressions for these two quantities, Q evaluated at R and Q evaluated at R plus dr. So conduction first. Okay, so how do we evaluate Q evaluated at R? We know we can use Fourier's law. Fourier's law. Fourier's law. What about Q evaluated at R plus dr? We don't really know how to evaluate the function at a different point, right? Like it's gonna be hard. It's hard to define. So because of this, we'll use a very useful, resourceful technique, which is a Taylor series expansion. So let us first define a Taylor series. Let me just erase here, make some space. Okay, so Taylor series. So all a Taylor series allows you to do is to predict or define a function at a point that you don't know based on the characteristics of that function at a point that you know. So the general formula for the Taylor series is the following. You have your dependent function, depends on x, and this is the function that you want to evaluate. This is the thing that you don't know, the new point that you don't know. You basically can define this new point based on the function at a previous point, or at a point that you know. So it's given by a sum of all the differential elements of that function. So it's the function itself. Well, let me just use a different. Okay, so it's y, it's the derivative, the nth derivative of y evaluated at the point that you know, let's call it x0 here, times the difference between the new point that you don't know minus the original point raised to the power of n divided by a factorial element, n factorial. Okay, this is just a fancy formula of saying if you know the function at a given point x0, you can find the function x evaluated at a new point x by doing this fancy sum. So this is, we can draw an analogy. Imagine you were a police officer and you were given, you had to predict the position of a suspect based on the position of the suspect at a previous time. So say another police officer was telling you the position of this suspect. Say the suspect could only go on a straight line. Imagine this was the straight line. Okay, imagine this is, let's call this y, I guess. And the suspect could move around this line. And all the police officer was telling you would be the velocity of your suspect and the position. So imagine this is just time and this is y, and you wanted to plot it. So say at time equals 0, the police officer tells you, okay, the suspect is at 2 meters along this line. So imagine this is 2 meters. So this is the initial position of the suspect. So let's draw here as well. So imagine the suspect is here. And the police officer is also telling you the velocity of the suspect. So he tells you, and the velocity of the suspect is 4 meters per second in the positive direction. So say, sorry, 2 meters per second in the positive direction. So imagine this is 1 second. Say this is seconds and this is meters. So he tells you it's 2 meters per second, and you can basically draw that velocity as a vector here. So kind of look like this, right? And so that means that 1 second later your suspect will probably be 4 meters away, right? So this is kind of what you would predict. However, the suspect might also have higher derivative terms. Not only a velocity, but he could also have an acceleration. He could also have a jerk. He could also have a pop. Yeah, I think I forgot the name of the other ones, but you know what I'm saying. The suspect could have higher derivative terms. He could decide to stop at any point. But basically, what you would want to do is to predict the position of the suspect at different times. So how confident would you feel predicting the position of the suspect, say 1 second later, say at this point, 1 second later? You'd probably say, okay, assuming that the suspect only has a constant velocity, you could predict him to be somewhere here, right? 1 second later, somewhere here. And I mean, 1 second later, it could be it's a completely fair assumption, completely fair estimation. What if you wanted to tell where the suspect is at, say, 60 seconds? Well, I guess you would probably say, okay, well, if I extrapolated that line, he could probably be up here somewhere. But you're completely not sure. It's very uncertain, because 60 seconds after, the suspect could have stopped, he could have gone back, he could have done many things. So I would be a lot less confident about this prediction than for this prediction. But what if you wanted to predict his position, say, at a fraction of a second, say somewhere here, say at 0.001 seconds? Then you'd be pretty confident that at 0.001 seconds, he's slightly displaced from his original position, and you would be a lot more confident to predict this position than this position. So here you're kind of using a Taylor series to predict the position or the function at a new point based on the function at a point that you already know. So how can we relate this back to the heat rate and stuff? Well, we can say that we can evaluate Q evaluated at R plus dr. So Q evaluated at R plus dr using this formula. However, same as the case with the suspect, we will only use the first derivative. So in this case it would be the velocity, but since the differential increment is so small, since the displacement here is so small, it's differential, it's infinitesimal, it could be okay to neglect the higher derivative terms. Say neglect the acceleration, the jerk, and the pop, and all of those, because if the time is so small, it doesn't really matter. It doesn't really matter. All you care about is the main component, which is the velocity, the higher derivative terms. And also notice that as your n increases, this denominator increases very fast, very fast. So it's definitely okay to just neglect all the higher order terms. So you can write that Q evaluated at R plus dr is just the original function, or the zeroth derivative, which is the original function, Q evaluated at R, which you know, plus the first derivative when n equals 1, Q, well, dq dr evaluated at R times the differential increase, or the difference between the new point and the old point. So R plus dr minus r just gives you dr, right? Dr plus, and you could keep going for n equals 2 and so on, but we will kind of neglect that just because of how small this is. So going back to the energy balance, we have in minus out equals 0, minus out equals 0, and for now we will just solve the conduction terms. So what's coming in? The only thing coming in the control volume is Q evaluated at R. What's coming out? From the conduction, we have Q evaluated at R plus dr, which we already solved for. It's right here, but let's write it down first. Q evaluated at R plus dr. And then what else is coming out? The convection term, dq convection, which we haven't solved for just yet. And this is all equal to 0. So let's replace this expression here for Q evaluated at R plus dr. This one, we'll just leave it the way it is. Minus parenthesis Q evaluated at R plus dq dr evaluated at R times dr minus dq convection, and this is equal to 0. So you notice here that we can cancel this term out with this one, and all we're left with is the derivative term. So we have minus dq by dr evaluated at R times dr minus dq convection equals 0. Okay, let's continue on this new tab. So how do we evaluate this differential element, this derivative term? We can pull out the minus d over dr, and then we can replace the expression for the heat rate that we already know how to express, which is the conduction heat rate, and that is expressed by Fourier's law. Let's do this here on the side. Minus, let me just use black again, minus d by dr, we pulled it out, and parenthesis, so Q evaluated at R, that's from Fourier's law, so we have that it's a minus thermal conductivity, K, of the fin, times the thermal gradient, dt by dr, times the area element. But this dt by dr is evaluated at R because this derivative is evaluated at R. So at R here, from our differential control volume, from the drawing, we are actually evaluating it at this inner surface, at this inner face here. So how do we express that area? Well, I always like to think about just an extended horizontal wall. So we can actually unroll this inner surface, this inner circle, and imagine extending a horizontal wall. And then, so what would the length of this wall be? It would exactly be the circumference of this inner radius, which is 2 pi r, right? Because it's evaluated at r. And then what is the height of the wall? The height of the wall is this thickness element. So then how do you calculate the area of the wall? It's just the product of its sides, and then the area would just be 2 pi r times t. 2 pi r t. So that's the area element. And then we also have a extra dr term that comes from a Taylor series expansion, and so we should add it here as well, dr, right? Well, maybe we should put it outside of the parenthesis, but it's the same thing. Let's put it outside of the parenthesis so that it's clear that this one comes from the Taylor series expansion. And then we need to also subtract the convection term, which we haven't solved for, but that is the next step. Here, minus dq convection equals 0. We can then introduce this derivative term. We can cancel the negative signs. So we have k. Let's put all the constants in front. We set constant properties, so the k is constant throughout the whole fin, even if the temperature varies. So we have 2 k pi t times then this derivative, notice that we have two terms that depend on the radius. We have, of course, the radius itself, and we have the temperature. So we have to do a product rule. You might recall the product rule. Let's actually write this down so that it's clearer. I don't want to skip steps. D by dr, and then we have dt dr times r, right? And then this is all multiplied by dr, then minus dq convection equals 0. Okay, so yeah, I didn't miss anything. Okay, so then the product rule, to use the product rule, you take the derivative of the first element and then multiply it by the untouched second element, and then you add the derivative of the second element, and then you multiply it by the first element without taking its derivative. So let's write that down. So we have 2k pi t times, so then the derivative of the first element, we actually take the second derivative of the temperature with respect to the radius, giving us d squared t over dr squared times r, right? Because we're multiplying it by the first element. And then we add the derivative of the second element, which is 1. The derivative of r with respect to dr is just 1, so that's just going to be dr, and then we multiply it by the first element, so we have dt by dr, and then this is all evaluated at r. I kind of didn't write it down, but here let's write it down. Evaluated at r, and then we multiply this by dr, and we subtract the convection term, and equals 0. Okay, now we will move over to the convection term. We must note that the convection occurs between two media. In this case, it's the surrounding air and the thin material. And opposed to conduction, convection also includes the advection heat transfer. That is due to the bulk velocity of the fluid. Conduction only depends on the diffusion within the material. And convection actually is the combination of the diffusion within the material. In this case, it would be the diffusion of the air at the boundary layer right on top of this surface, and the advection heat rate that depends on the bulk velocity of the air. However, I will go into more depth when we reach the convection part of the course. But for now, all you need to know is that the convection heat rate is expressed by Newton's law of cooling, which groups these two variables, the advection and the diffusion, into a single coefficient. It's called the thermal coefficient, the heat transfer coefficient, H, and it depends also on the difference of the temperatures of the surface and the bulk fluid, so this T infinity. So let's express it mathematically. We can express dq convection, which is actually leaving the system, as temperature, the difference of the surface temperature and the temperature of the bulk fluid, so T minus T infinity, times H, the heat transfer coefficient, and then we also need to include the area at which this heat transfer occurs. In this case, the exposed area to the surrounding air is this top area and the bottom area, which are exactly the same, but we can't forget that it's both of these areas that are exposed, this top area here and the bottom one. And then how do we express this area? Well, we can express it as the difference between the area of two circles, one where the radius is r and the other one where the radius is r plus dr. So you know that the formula for the radius for the area of a circle is pi r squared. So let me just express this as dA. This area term is differential because the thickness of this area is actually differential as well. You may recall it's dr here. This thickness is dr. So that's why the heat rate is actually a differential term as well. Depends on the area, and the area is differential anyway. So let's express the area, dA. We can call it dAs, or surface area. dAs is just going to be the area of the big circle, which is pi r plus dr squared. We can take a common factor of the of pi, and then we subtract the inner radius squared, r squared. Okay, so let's expand this perfect square. We get pi r squared plus 2 r dr plus dr squared minus r squared. Okay, so here we can cancel out this r squares, and we're left off with 2r dr and then this dr squared term. However, notice that this dr squared is very small. We actually truncated the Taylor series for the first derivative terms, or the ones that included this dr, meaning that the rest we said that was negligible. So in this case we can get rid of this term as well. So this is equal to 0. Well, approximately equal. It's not quite equal to 0, but for our purposes and for the scope of this course it will. So here we have 2 pi r vr, and then also remember that this would be for only one face, but we have to multiply this whole thing by 2. So here, I forgot, here, and then we have here 2 times 2, okay, dAs. So then dAs is just going to be 4 pi r dr. And now we can express this dq convection the following way. So dq convection is just going to be 4 pi r h t minus t infinity times dr. Okay, and now we can plug it in our energy balance. We can plug it in here, and we're going to have 2 pi kt squared times r plus dt dr evaluated at r times dr minus, and then it's this whole thing, 4 pi r h t minus t infinity, and dr equals 0. So it's always a great thing when you notice that you have a dr term that you can cancel out and you can take out of the differential balance. This indicates that you're doing the right thing. So you have always to look for things that you can cancel out once you derive your differential equation. It's usually this differential terms. So let's get rid of this dr and this dr. We can also divide the whole formula by 2 pi, so that we can cancel this one out, by k and by t as well, and by r. So basically divide the whole thing by the minimum common factor, let's say. So in this case it's 2 pi kr, and then let's also divide by t so that we can get rid of any of the constants in front of this first term here. So we have d squared t by dr squared. We also divided by r, so notice we won't have the r here, plus 1 over r times dt dr minus, so 4 divided by 2, it's 2. Then we also divided by r, so the r goes away. We have an h here. We also have a k. We also have a t. I think that's it. T minus t infinity. And this is equal to 0. So we're almost done with our differential equation. Now we need to simplify it a little bit. We need to get rid of this non-homogeneousness, however you say that. So it's non-homogeneous because there's a constant term that screws everything up. However, if we can get rid of this constant term, we have a homogeneous differential equation that is solvable, and it's actually quite easy. So to bypass this problem, we can notice that this bulk temperature, this T infinity, is actually constant. It doesn't vary with respect to the radius. It doesn't vary with respect to anything. So we can sort of include it in a new variable that is actually called the excess temperature, and in the book they call it as theta, and they express it as the difference between the temperature at whatever point. Remember that this temperature depends on R, so it's the temperature at whatever point minus the bulk temperature of the fluid. So we call it this T minus T infinity, and this variable also depends on R because this temperature depends on R. However, this bulk fluid temperature is constant, so when we take the derivative of theta with respect to R, we are just going to get the derivative of the temperature with respect to R. So this change of variables is very beneficial for us because it gets rid of the non-homogeneousness, or it makes the differential equation homogeneous. We can also group up all these constants and call this m squared. You'll see why in a second. So these are just sort of definitions that we're using for convenience. So so these are sort of definitions we're using. And then we also said that m squared would be 2h over kt, right? And now we have our final differential equation by replacing these variables with these new variables that we are using. So we would have d squared theta by dr squared plus 1 over r d theta by dr minus m squared theta. I almost wrote again t minus t infinity. Okay, so this is equal to 0. Notice that this differential equation is homogeneous because we don't have any constant term. Every term here depends on the radial component, and so it is solvable now. Okay, so now we have our differential equation. Now what is the solution for this differential equation? The way that you would find it is basically looking at the formula sheet. You don't need to know the solutions by heart. I actually made that mistake when I was taking this course. I thought that the solutions were not in the formula sheet, and I actually went into the final and I knew most of them by heart. And then on the final I saw a new differential equation that I had never seen before, so I was not able to solve it because I didn't know, I had never seen it before, so I didn't even know what the solution was. But the reality was that all the solutions you need are actually in the formula sheet. Right here I cropped the section that has all those solutions to the differential equations, and in this case the solution for this particular equation is a modified Bessel function. Bessel functions are basically like trig functions. They're cyclical, and they come from infinite sums. You don't need to really understand the nature of these functions nor their behavior, but you need to know certain certain characteristics of these functions, especially when they are evaluated at 0. Some of them become infinity when they are evaluated at 0, or some of them become even complex infinity. I won't go through these cases right here, and we won't really need that because if you see, the smallest point at which we will evaluate these functions are basically at this inner radius, which is not equal to 0. So we shouldn't have any of those undefined problems, or problems that will give us an undefined or an undefined solution. So let's write it down for this case. So theta, or the temperature, the excess temperature, is equal to C1. So this is a Bessel function of 0th order, the modified Bessel function of 0th order, times r plus c2 k0. This is the other modified Bessel function of 0th order. Okay, and this m's here, notice that they are the square root of this m squared. Okay, something that I forgot to say is that the solution for this differential equations depends on, it's very important that you have the right sign here and the right coefficient here, because the solution will depend on this sign and this coefficient. So you have to watch out for that. Okay, so this is our solution. Notice that we have two constants that we don't know yet. This constants will be solved using the boundary conditions of the problem, which will be the next step. However, let's actually solve for the derivative of this solution, and the derivatives you can find over here at the bottom. So when you take the first derivative, sometimes the sign changes. They actually kind of behave like a trig function, so sometimes there's a negative sign that comes in. So let's actually find what the derivative would be. So it's actually d theta by dr would be equal to, so we have here again chain rule, so Cm, we can pull out the m for both of the terms, and then we would have C1 I1, this is the derivative of I0 mr, minus, so this one has a negative sign, C2 K1 mr. Okay, so now we have the zeroth derivative and the first derivative, which is all we need to plug into our boundary conditions. So okay, now we can actually go into the boundary conditions. Let me write it down. Boundary conditions. So boundary conditions are basically conditions that you know about the problem, and they are evaluated at the edges of whatever direction your temperature depends on. So the first edge would be at this inner surface here, right? And the other one would be here at the outer edge of the fin, at the tip. Right, so let's first go over the boundary condition at this inner surface, at this circular ring here. So the first boundary condition would be at the base, and we know that at the base we know the temperature. So theta evaluated at Ri, this is Ri, this inner radius, Ri is equal to theta b, or the base excess temperature. Notice that the actual boundary condition without changing variables would just be here. I'll just do it here on the right. It would just be T evaluated at Ri equals Tb. However, if we add a minus T infinity in both sides, we get the excess temperature equivalent. Okay, so now the second one. The second one is at the tip, at the edge, and here we have really two options. We can evaluate the heat loss. We can evaluate it as a heat loss at the outer edge, meaning that heat is leaving through this surface, right? And to do that, we would express it as follows. So we would say that the convection heat loss to the ambient air through this surface is equal to the conduction heat rate going through the surface right before. So I guess this is conduction, and this would be convection. So at this point, conduction and convection are equal. So we can express it as, here I'll write conduction equals convection. And notice that this is the real boundary condition. However, it actually complicates the problem a great deal, and you'll see why. So we would have minus k times, here we can do a flux balance as well, because the areas, the cross-sectional areas are the same. The conduction area is the same as the convection area, so they can cancel out. So we are left off with dt by dr evaluated, actually we're using theta here, so d theta by dr evaluated at RO of the outer radius is equal to h times theta evaluated at the at the outer radius. Okay, so we can put these two together and we have d theta by dr evaluated at RO equals minus h over k times theta RO. Okay, so this is the most legit boundary condition at the edge, but as I said, it complicates the problem. Let me just write it down with temperature terms. It's going to be minus k dt by dr RO equals h times t minus t infinity. And then this is at RO. Okay, so these are two boundary conditions. And then, as I said before, there's another boundary condition that we could have used instead at this outer edge that could simplify the solution to the problem, but that is not quite accurate. And this boundary condition is assuming that the outer edge is actually adiabatic. Why would this be a reasonable assumption? Well, remember at the beginning of the video that we assumed that this thickness was negligible with respect to the radius. Well, that means that this area term will also be certainly negligible, and then the heat rate, which depends on the area, will also be negligible coming out of this surface. So basically, if we wanted to express this as an adiabatic, we just write it here, adiabatic tip, we would have d theta by dr at RO equals 0. So you might notice that this boundary condition is not quite accurate. The one that you should write on a test is always this one, because Professor Servio rarely asks you for the final temperature profile, for the final equation of the temperature profile, and that is what's really complicated about this boundary condition. But for the test purpose, you will always write the most accurate one. And then for the adiabatic tip, case, we would have the following solution. Okay, so this is the final solution using those two boundary conditions. So final temperature profile. By the way, you can access this solution or this equation on page 167 of Fundamentals of Heat and Mass Transfer, the 7th edition by Incorpora and DeWitt, which is the book that you use for this course with Professor Servio. So now that we have the temperature profile, we can solve for the heat rate, and there are multiple ways that we can solve for the heat rate. Professor Servio usually likes to ask for different ways of solving the heat rate or expressing that heat rate going through the whole fin, and usually one of the solutions is from the conduction heat rate that occurs here at this inner surface, because whatever comes in here through this inner surface has to come out through the whole fin. So basically you can express the heat rate that the fin dissipates by the conduction heat rate that occurs in this interface between the pipe and the fin. So the actual expression is actually QF. So QF is equal to this inner surface, which is equal to, as we said before, the horizontal rectangle unrolling this inner ring into, you know, a horizontal wall gives us 2 pi r, 2 pi ri t, that's the area term, and then we multiply that. There's a minus sign from Fourier's law, because this is the conduction heat rate, k d theta by dr evaluated at Ri. So you'd basically plug in the derivative of this temperature profile, and then you would replace this R terms with the Ri. You're evaluating it at Ri here, and then that would give you the heat rate throughout the whole fin when you multiply that term by K and by the area. Another way for solving for the heat rate is actually from integrating this whole surface, the whole surface exposed to the ambient air of the fin, which is exactly this top surface and the bottom surface, as well as the edge, depending on what boundary condition you chose to use. In this case, since we said that the boundary condition was adiabatic at the tip, we assumed that there was no heat flowing out through here. So that means that the heat rate would only be the integral over the top and the bottom surfaces, and we express the integral using Newton's law of cooling. So it would be h times the integral going from Ri, the inner radius, to the outer radius of theta, or the excess temperature, that depends on R, times the differential area element of that top and bottom surfaces. So it's 2 pi r dr, this is the Jacobian, and this is the integral of the angle theta over the whole 360 degrees, or 2 pi, so it becomes 2 pi. And yeah, so that would be the heat rate if we neglect the heat loss at the outer surface. However, if we were to include it, say we use this boundary condition instead, this boundary condition here, we would express the heat rate. Also notice there's a factor of 2 here that we should add because we have the top and the bottom surfaces. Okay, and then if we were to include, okay, this one would be including heat loss at tip. So including the heat loss at the tip, we would have this same term here from the top and the bottom surfaces, so 2h integral from Ri to Ro of theta, that depends on R, times 2 pi r dr. Then we would also add the heat loss that occurs at the surface, at this edge here, and we can express the heat loss here in 2 different ways, the conduction or the convection way, which are exactly the same, which are equal, but expressing it from the convection, in the convection way, we would just say h times the outer area, 2 pi ro t, times theta evaluated at ro. This is the convection expression. And then here we can have or minus k, just scroll down, or minus k times d theta dr evaluated at ro times the area element, which is the 2 pi rot. Here this is or, because this second term here we can express it in 2 different ways. So we've reached the end of the video. We've solved for the heat rate dissipated by the fin, and well, we'd say 2 different ways or 3 different ways if we were to express this 2 different second terms as independent ways, but they're actually quite the same. So yeah, we found 2 ways of expressing it. We also solved for the temperature profile using a modified boundary condition, but remember that in a test, you should always write the accurate boundary condition, because Professor Servia will rarely ask you for the temperature profile, or he will rarely ask you to solve for the constants C1 and C2. So you should always use this two boundary conditions. Please let me know if something was not clear, if I forgot to say anything, if I made any mistakes. I will see you on my next video on thermal circuits, and leave any comments below. Thank you.